equation, which is the equation of the form ax square y double dash plus bxy dash plus cxy is equals to 0. So whenever such a equation is given where a, b and c are numbers, so in that case we shall use this method, and this method, the method is we shall try this trial solution, that is x power m, and that we will substitute here and we'll get characteristic polynomial for this method will be am square plus b minus am plus c is equals to 0. So whenever such equation is given, we shall find out what is coefficient of x square y double dash, that is a, coefficient of x dash xy dash is b, and coefficient of y term is c. So finding a, b and c and substituting it in the characteristic polynomial gives us the characteristic roots. So here characteristic roots are m1 and m2. So depending on these values of m1 and m2, if they are distinct, we will get the general solution in the first case, that is c1 x power m1 plus c2 x power m2. When we have a repeated characteristic roots, in that case we will get the solution to be x power m plus another constant times x power log x times x power m. Right, so this is the general solution whenever we have a m1 is a repeated root of the characteristic polynomial. And in third case, whenever we have a pair of complex conjugate roots of the characteristic polynomial, in that case we have this as a general solution. Okay, so we started one example, that is x square y double dash minus 2xy dash plus 2y is equals to x power 3, and we want to solve it for x greater than 0, and corresponding. So whenever we compare the given equation, first we make it to homogeneous equation by considering the right hand side to be 0, right? And then this is the Euler-Cauchy homogeneous equation. So first we'll find out what is the corresponding characteristic polynomial. So here a is 1, b is minus 2, and c is 2, right? So that we have substituted in this polynomial, we got characteristic polynomial corresponding to the given example, given differential equation. And then we can easily check that it has these two different roots. So since it has a two different characteristic roots, the first case will give us the solution. So solution is c1 y1x. y1 we are taking x function, y2 we are taking x square function, right? Because y1 is x power m1, m1 is 1, and y2 is x power m2, m2 is 2, is m2, and m1 and m2 are two different roots. That is giving us two independent solutions, y1 and y2. So this is the general solution of homogeneous part. But now we want to find the non-homogeneous solution of the non-homogeneous equation, right? So for solution of the non-homogeneous equation, we know that we can apply the variation of parameter method, and variation of parameter method we can apply only when the coefficient of y dash in the equation we have to convert into 1. So the given equation is this equation where coefficient of y double dash is x square. So to make coefficient of y double dash 1, we have divided the equation into x square, and we got this differential equation. The goal is to find general particular solution of this non-homogeneous equation. So let us start with that today. So consider or compare the non-homogeneous equation compare the non-homogeneous equation. Which is y double dash minus 2y dash divided by x plus 2 by x square. Y is equals to x with our standard equation, non-homogeneous equation, that is y double dash plus exy dash plus 2xy is equals to fx. If we compare with this, we get the right hand side function, which is x, right? So right hand side function is x for this particular differential equation. And what else we need is, we also know that y1 is x square, y1 is x, and y2 is x square. So to apply the variation of parameter method, we need to find the Wronskian. So Wronskian is y1, y2, y1 dash, y2 dash. So that is x square. Derivative of x is 1. Derivative of x square is 2 times x. So simplifying this will give us 2x square minus x square, that is x square. And x square is non-zero because in our differential equation it is mentioned that x is positive. Fine. So now from the variation of parameter method, therefore the particular solution of this non-homogeneous equation is, so the formula, if you recall, the formula is yp is equals to minus y1 integration y2 right hand side function divided by Wronskian integration of that plus y2 function is outside, y1 function is inside, fx divided by Wronskian. So we know all these values. Y1 is x, y2 is x square, Wronskian is x square, and fx is x. So let us substitute all these values here. So we get minus x integration, y2 function is x square, fx function is x divided by Wronskian plus y2 function is x square integral y1 function is x, fx is x, Wronskian is x square, right? So we substituted all the values according to this particular example, and now we know that some of these terms will cancel out. So essentially we shall get minus x and integral of x, so that is x square by 2 plus x square times integral of 1, so that is x, right? So now this is nothing but x power 3 we can take common, and 1 minus half, so that means half x power 3. That is our particular solution of the non-homogeneous equation. So we got general solution of the homogeneous equation and particular solution of the non-homogeneous equation. So now we can write down the general solution of the homogeneous equation. So therefore general solution of the given non-homogeneous differential equation is yx equals to solution of the homogeneous part plus particular solution. So solution of the homogeneous part, we know that y1 and y2 are x and x square. So that means it is c1x plus c2x square plus particular solution, which is x cubed by 2. Right. So this is a general solution of this Euler non-homogeneous Euler-Cauchy equation. Yeah, so one example of solution of non-homogeneous equation we have already discussed earlier. Whenever we have a differential equation with a constant coefficient. But here we have a second order differential equation in the Euler-Cauchy form. Right. So now one last topic in this particular method we want to discuss is regarding constant differential equation with constant coefficient of the higher order. Homogeneous case. Ordinary differential equations. Yeah, so whenever we have higher order ordinary differential equation, how do we solve such equation, particularly when the equation is given to be homogeneous? So first, we shall only discuss the differential equation with the constant coefficients. So if we are given differential equation of nth order linear equation with constant coefficients. So such equation is given, then we can do, we know that whenever we are given nth order ordinary differential equation with constant coefficient, we shall find corresponding characteristic polynomial Tm, right? And depending on what are the roots of the corresponding characteristic polynomial, we have three cases. First case is yeah, so here instead of having the cases, we have 3 points. So first point is that if we have distinct roots of the polynomial, so suppose lambda 1, lambda 2, lambda n, or in other words, suppose we have m1, m2, m1, mn are distinct and distinct roots of the characteristic polynomial. Then we know that the way we are finding general solution, here also we can find general solution, and the general solution is yx equals to c1 e power m1x, c2 e power m2x, and cn e power mnx. Right. So whenever we have distinct roots, it is simple. The same way, if we have a repeated roots, so suppose some particular root is repeating, so here the root may repeat more than 2 times because this is nth order differential equation. So suppose our first root, in general we can take mk, but suppose m1 is a repeated root of the characteristic polynomial, and it has multiplicity k, right? So that means k times it is repeating. So that means they have a factor of m minus m1 power k of the polynomial. So in this case, the corresponding solution will be e power m1x for all these k times, right? So that means we need to find independent k roots. In this case, instead of getting e power m1x, e power m1x, e power m1x k times, because these all functions are same, instead of that, what we will do is we will find the independent solution, and that we know that the corresponding independent solution is this set. X power k minus 1 e power m1x, right? So in this case, we get this many Li solution corresponding Li solutions of the given homogeneous equation. And the third case is complex case. Third type of case is complex case. So whenever our root m1 is complex root, the complex roots are comes always in the pair. So if one root is complex root, then there is always a corresponding root which is complex conjugate. So we get another
So,
root. Yes.
sir, in the above case, if m1 is a root with multiplicity k and m2 is a root with some other multiplicity,
Yeah. So
so
correspondingly, we will get Li solutions. So suppose M2 has a multiplicity L, then the corresponding L roots will be e power M2x, x e power M2x, x square e power M2x, up to L minus 1 power of x.
okay, sir.
Right. So we'll see some examples afterwards. At least of the third order and fourth order, we will see some examples. So we get corresponding complex conjugate. We get M2, which is another root, and M2 is complex conjugate of M1. Right. So suppose M1 is basically alpha plus I beta, where alpha beta are real numbers. Then M2 will be conjugate of this. So in this case, corresponding Li solution are, so you know that whenever we have such a complex conjugate roots, the corresponding roots, corresponding functions, Li functions are e power alpha x, cosine beta x, and e power alpha x, sin beta x. All right. So basically, what this result says that as many repeated roots, as many distinct roots we have, as many Li functions we can find. Right. So that means since the differential equation is nth order differential equation, we can always find n Li vectors. So let us see some simple examples. First example is that whenever we have we are given differential equation, find general solution of the third order differential equation, that is y triple dash minus 6y double dash plus 11y dash minus 6y is equals to 0. So this is a third order differential equation. That means we need to find 3 independent solutions. And for that, first of all, we need to find the corresponding polynomial. So this is the third order linear differential equation with the constant coefficients. So the corresponding polynomial will be 1 times m power 3 minus 6 times m square, 11 times m, and minus 6. So this is our characteristic polynomial. All right, so we can easily check the roots of this characteristic polynomial are. So this is a third order polynomial of third degree. So that means we will get 3 different roots. The roots are m is equals to 1, 2, and 3. Right. So here basically we have 3 different roots we are getting. First root we are getting m1 is 1. Second root we are getting m2 is 2. Third root is m3 is 3, and this all roots are distinct. So therefore the general solution, we know whenever we have a distinct roots, we shall write down the solution in power of e power mix. Right. So first is e power m1x, m1 is 1. C2 e power m2x, m2 is 2. C3 power m3x, m3 is 3. So in this case, because all the roots are different, we got this particular solution as a general solution of the homogeneous equation. Now let us discuss the case of the repeated roots. So when we have polynomial, we want to solve the differential equation y triple dash minus 2y double dash plus y dash equals to 0. So in this case, the corresponding characteristic polynomial will be m power 3 minus 2m square plus m. There is no constant term, there is no y term, right? So from this itself, we can easily see that the polynomial is this one, and its roots, at least one root is 0, right? And the roots of this polynomial are, first root is 0, and if we take m common, it is the square, perfect square, that is m minus 1 square, right? So we have 2 other roots which is repeated, 1 and 1. So now we can see that the roots are distinct, 0 and 1, but 1 is repeating. So therefore the general solution is yx is equals to, the first root is c1 e power 0x, right? That is m1x, plus second root is c2 e power 1x. Now third root is same because these two are repeated roots. So now what we shall do, we can't take e power 1x. So we know that whenever we have repeated roots, we take the next root to be x times this root, right? So that we will use here. So as many times it is repeating, we will multiply 1 by 1 x times. So that is x e power x. So let us write down this finally. What we will get is c1 e power 0x is 1, c2 e power x, plus this should be c3. third constant, x e power x, right? So in this case, we will get this solution. Now, final case we want to discuss is complex case. So here we have, let us say we have differential equation of the fourth order. So fourth derivative of y plus 2y double dash plus y is equals to 0. So this we can also write in earlier notation what we have defined, fourth derivative of y plus 2 second derivative of y plus y is 0, right? This is another notation. Okay, so we want to solve this differential equation. So first the corresponding characteristic polynomial is okay. So here polynomial will be of fourth degree, right? M power 4 plus 2 m square plus m is equals to 0. Not m, it is a constant term, right?
Yes.
Right, yeah. So yeah, so now it is fine. Okay, so now we can see that if we substitute m square equals to t, then this is a perfect square, and that means we will get two values of m square, and then we'll take square root of that. Yeah, so m square will be -1, and that means we'll get four roots which are complex numbers. So therefore the roots are m1 is equals to I, m2 is equals to -I, m3 is equals to I, m4 is equals to -I. Two roots are same, two roots are the other two roots are also same, -I and -I. And then we know that if complex root is, so what will be corresponding to m1? So that is alpha plus I beta. So alpha is 0, beta is 1. So that means e power alpha x cos beta x. Beta is 1. So that means we'll get cos x function. Right. And the same way for m2 we will get m2 is -I. So that will get sin x. Now m3 is I, and we have seen corresponding to I, the solution we will get is cos x. But cos x I cannot take because we already taken cos x. So again here the roots are repeating. So we shall take cos x cos x. So that means we can check that cos x and x cos x are independent using Wronskian. Similarly, sin x, and we get x sin x. Right. So the goal is that as many roots are there, we need as many independent solutions. So therefore, general solution is yx is equals to c1. First is cos x function plus second constant times sin x, third constant times x cos x plus fourth constant times x sin x. So here we can see that basically kind of case 2 and case 3 combination we are using, because the roots are complex as well as they're repeating. Okay, so that's all regarding the homogeneous differential equation with the constant coefficients. So now we want to start a new method which is known as the power series solution. if you recall, earlier we used Picard's iteration, and using the Picard's iteration, we have observed that the solution we can write as a limit of a polynomials, and that is nothing but the power series of e power x function, e power x or e power minus x. So that gives us idea that it may be possible to solve a differential equation using power series. So that is this method. So every time we assume that some function is a solution, and then we find out what is that function. So this is also the same method. So power series method to solve differential equations. So this method is a general method. It can be applied for first order differential equation also, second order also, and higher order also. So first of all, let us recall the notion of radius of convergence, because we are discussing series. So if we have a non-zero number p, find values of x for which the series. So we are given a series n running from 1 to infinity, p minus 1, p minus 2 up to p minus n plus 1 divided by n factorial times x power n. So we need to find all possible values of x for which the series converges or diverges. Right. So if you recall that we have already studied one method in the previous semester, the method is how to find the radius of convergence of the given power series. It is called power series because it is in powers of x. And whenever we have a power series, to find for which values of x it converges, we use ratio test or root test with the modulus sign. So let us start by writing the nth term first. So here nth term is p minus 1, p minus 2 up to p minus n plus 1 divided by n factorial x power n. So this is our nth term. So we want to apply ratio test. So we shall first find what is n plus 1th term. So just substituting n plus 1 instead of n, we shall get. So here we have minus n plus 1 plus 1. So that means we'll get up to p minus n and x power n plus 1. Right. So now we shall find the ratio. So therefore we get limit n tends to infinity modulus an plus 1 by an. So what is the ratio test? Ratio test is the given series converges whenever this ratio is less than 1, and it diverges whenever this ratio is greater than 1. Right. So first let us find out what is this particular limit for this example, and then we'll use this condition whenever it is less than 1 and whenever it is greater than 1. So here we know what is an plus 1. An plus 1 is p minus 1, p minus 2 up to p minus n divided by n plus 1 factorial into x power n plus 1 into inverse of an. So that is n factorial divided by p minus 1, p minus 2 up to p minus n plus 1 and 1 upon x power n modulus of that. Right. Yeah, so let me write down here x power n. Okay. So now we can see that we can cancel x power n. X will remain. This n factorial will cancel out, and all other terms will cancel out except p minus n. Right. So all this term will cancel out. Only p minus n will remain. So this is nothing but limit n tends to infinity p minus n divided by n plus 1 into x modulus of this. Right. So now we know that whenever we want to find limit n tends to infinity, p is a fixed number and x is also a fixed number which we are going to determine. So we can rewrite this as limit n tends to infinity dividing by n. So this will be p by n minus 1 plus 1 by n times x, taking limit inside. So p by n and 1 by n will be 0. Modulus of minus 1 is 1. So essentially we get mod x. Right. So what is this limit of the ratio? Limit of the ratio is mod x. And whenever this ratio is less than 1, the series converges. Right. So therefore, for mod x less than 1, the series converges. And for mod x greater than 1, the series diverges. And basically we are using here ratio test. So whenever we have a power series, we can use ratio test and we can identify where the series is convergent or divergent. And why we need the convergence and divergence of the series? Because the series is convergent, that means, so suppose we have a series summation n is equals to 0 to infinity an x power n. Suppose this series is given. So what is meaning of that? This means if we expand, it is a0 plus a1x a2x square and so on. So the series converges means this sum is a finite number. So every time it may not be finite number. We know that if we add 1 plus 1 plus 1 plus and so on, it may be it is actually infinite. If we add 1 infinitely many times. Yeah. So therefore it is important that this sum is a finite or not. And that is this result that we can find the series converges for mod x less than some number r. So whenever the series converges, we can differentiate it. So if we differentiate this series, what we get? We get a1 plus 2a2 x square plus 3a3 x square and so on. Right. So that series, if we write in the summation form, it is summation n1 to infinity n an x power n minus 1. Right. So whenever the given series in this notation, we want to find its derivative. So we shall assume that given differential equation has solution yx. Right. If yx is this, then what will be the derivative of yx? The derivative will be, instead of starting from 0, the first term has been cancelled here. Right. There is no a0 term. So therefore the summation will start from 1 right? And this power will decrease by 1, right? So a1x has become a1. So what shall
So
be the,
when do we have to assume this solution? Means the one you are telling, when we have to use this?
yeah, that I will explain in the example. First I am explaining the notation. So whenever we have such a series, its derivative will be this one, right? So what is the change? N is 0. Instead of that, we started n is equals to 1, and this general term we can differentiate in this way, right? Similarly, we can write down the second derivative. Yeah, so it will be more clear if we will take some examples. So let us take an example. So consider the initial value problem. So we are given first order differential equation, that is 1 plus x y dash is equals to py. The initial condition is y0 is equals to 1, right? And what is p? P is a constant. So now we'll see that what do we mean by power series method. So we are given this first order differential equation. We want to find its solution yx, and that solution is satisfying this condition, initial condition. So what we'll do is we'll assume that the given differential equation has a power series solution yx is equals to summation an x power n, right? So what we are doing, we have assumed that this is a solution of given differential equation. So now what is the goal? Goal is to find these constants using this equation, right? So we are assuming some power series is a solution, and essentially we'll find an. So we'll exactly get what is the actual series and whether that series represents some function or not. So let us solve this. So first thing, we need to substitute y and y dash here. So y we know what is y dash. We already found y dash. Y dash is summation 1 to infinity 10 an x power n minus 1, right? So this is our y dash, this is our y. We'll substitute y and y dash in this equation, and then we'll find out the constant. So substituting y and y dash in the equation, 1 plus x y dash is equals to py. So what shall we get? So we shall get 1 plus x times y dash. So what is the series of y dash? Series of y dash is n an x power n minus 1 summation 0 to infinity, sorry, 1 to infinity, because it is derivative, so it will start from 1 to infinity, is equals to p times the given series, that is 0 to infinity an x power n. Right, so now we can simplify this. So we shall get the first series is n an x power n minus 1, 1 to infinity, plus x times this series. So x times series is n is equals to 1 to infinity n an x power n, and this term we can take on the other side. It will be minus 0 to infinity p an x power n is equals to 0, right? So now from this series we shall write down the terms one by one. What will be the constant term we can equate, we can find out. So what will be the uh, yeah, so for more clarity, let us keep the other term on the other side. So what will be the constant term on the left side? So if you see that this series starting from n is equals to 1, right? So all the terms will be x, x square, x cube, so on. But here we shall actually get the constant term. So if we take n is equals to 1, the power of x will be 1 minus 1. So that equals x power 0 is 1. So the constant term, if we compare constant term both the sides. So left side constant term is for n is equals to 1. So that is a1. Right side constant term is when n is 0. So n is 0 means we have p times a0. Right. So we got a1 term in terms of a0. Now both the sides compare coefficient of x. So coefficient of x in this series we need to substitute n is equals to 2, right? So we get 2a2, right? And here coefficient of x we need, then we need to substitute n is equals to 1. So we get a1 is equals to, here again for x term we need n is equals to 1. So we get this one. So now what, using this, what we can write? We can write a2 in terms of a1. So what will be that? That will be p minus 1. This term will go on the other side, divided by 2 a1. Right. So a2, now we have iterative formula we are getting. So we can write a2 in terms of a1, and a1 we already know, that is p times a0. So this is p minus 1 by 2 a0. Right. So this way, if we compare the nth term, what shall we get? Both the side. So comparing coefficient of x power n. So what shall we get? So left side, if we want x power n term, we need to substitute n plus 1 instead of n, right? Here coefficient of x power n is n an is equals to, right hand side we have pan, right? So now we can write the an plus 1th formula in terms of an, and that is nothing but p minus n divided by n plus 1 times an. So this is the main step. We shall be using this every time in finding the nth coefficient. So such a formula is called recursion formula, and using recursion formula we can find all n. For example, we know a2, so if we substitute n is equals to 2 in the recursion formula, one. So if we substitute n is equals to 2, what we get? We get a3. So a3 is p minus 2 divided by 3 times a2, and we already know a2 is p minus 1 by 2 into a0. So now we can write this formula very nicely as p minus 1 p minus 2 divided by p factorial a0. Right. Similarly, we can find a4 and all that. So now what is the, therefore we shall get the nth term an to be, what will be the nth term? Now we can guess that, because a1 is p times a0, a2 is p minus 1 by 2 a0, this is p minus 1 p minus 2 by 3 factorial a0. So nth term will be p minus 1 up to p minus n plus 1 divided by n factorial times a0. Right. And what is a0? So we know that yx, yeah, so we assume that yx is equals to this power series satisfies initial condition. So that is y0 is 1. So y0 is 1, that means we get, if you substitute y is equals to 0, we get a0. So a0 is 1. Right. So therefore the solution is yx is equals to summation an x power n, and in that we found an is this term where a0 is 1. So that means an is this term basically. Right. So that is p minus 1 divided by n factorial x power n. So basically this is the solution of the given differential equation. Okay, so I think let me stop here.